Assalamualaikum. My name is Siti BALQIS binti JAMIL. My metric number is F25A1619. Today I'm to present an innovative agrotech project titled the Harmonized Mango Grow Rate Optimizer. As we all know, the premium harmonized mango cultivate in Perlis, Malaysia, demand precision cultivation to successfully achieve export quality standard. A major challenge for agrotechnologists and farmers is determining the exact timing for optimal fertilization, specifically for nitrogen and potassium, as well as pinpointing the perfect window for protective bagging to prevent devastating fruit fly attacks. This is where our application comes into play, bridging the gap by leveraging an advanced mathematical approach, specifically calculus, to solve a real-world agriculture industry challenge. So how do we measure and track the weight development of the mango? According to biological data, fruit weight development curve. Please refer to the formula displayed on the screen. Our core weight function is modeled as fx equal L over 1 plus T power negative K x negative x0, which gives us the characteristic S-shaped growth curve. To calculate the absolute growth rate, we take the first derivative of the function expressed as SFX. Through this interactive app, we have calibrated the model parameters using authentic local data. Max capacity L 400 gram representing the target maximum fruit weight. Growth rate scale K 0.08, inflection point X0, 60 DAA, which stand for day after interface or day post-pollination. Next, let's take a look at the interactive cultivation chart. The solid green line represents the mango weight fx in gram, while the dashed red line tracks the growth rate fx in gram per day. The app features a live scale interface. For instance, if we inspect the 60 DAA, the mango weight reaches exactly 200.00 gram and the growth rate is hit its absolute peak at 8.00 gram per day. Mathematically, this is the point of inflection, where the second derivative equals 0 fx. This big growth-based demand critical agrotech action. Soil management must be tightly controlled. Any water deficit right now will severely stunt the final export size, while a sudden deluge of water will cause devastating rainmaking. To guarantee that this application delivers practical value rather than just theoretical concept, the model curve are fully calibrated based on Morphological Development Index published by prominent Malaysian agrotechnology institutions. Number 1, Mardi Research Journal Vol 32, specifically regarding the physicochemical change of harmonized mangoes during development. Number 2, Technologies Mango harmonized by the Department of Agriculture, Perlis, utilizing their federal guideline for harmonized husbandry and ripening schedule. In conclusion, how do we apply this derivative practically to an agrotech curriculum or real-world farming? We focus on 3 core applications. Number 1, inflection point finder. By identifying the maximum point on the fx curve, which hit its absolute peak at 8.00 gram per day on day 60. We mark the exact transition point of fx where the fruit shift from accelerating weight gain to decelerating development. Number 2, resource allocation. By aligning high growth rate periods where fx greater than 5.0 spanning day 40 to 80 DAA with irrigation model. farm can conserve massive quantities of water during early phase and target irrigation perfectly when the fruit requires them slowly. Number 3, harvest window predictor. When the first derivative fx approach 0.08 day 100 and beyond, the mango is entering commercial maturity. At this stage, starch is actively converting into sugar, rendering the fresh wheat ready for selecting and picking. Overall, this application proves that intersecting data science, mathematics, and agriculture is successfully.
Hi guys, my name Muhammad FAKRUL Iman bin Amin. My matrix number F25A1575, and this is my presentation for prediction optimum agronomic intervention using first derivation for MD2 pineapple. Here is our real world problem. In area like Pontian, MD2 pineapple grow on highly acidic peat soil. These soils suffer from severe nutrient leaching. If a farmer apply expensive coastal fertilizer too early, the roots can absorb them and the nutrition wash away. If they apply them too late, the plant growth has already slowed down. To solve this financial and environment waste, we need to find the exact biologic window where the plant hunger is at its absolute peak. The logistic curve graph moving upward in an S shape pair with its first derivative curve, a bell curve speaking in the middle, equation side by side, fx biomass versus fx growth rate. The map is, we use a logistic cron function, fx, which track cumulative biomass up to target harvest weight of 2000 grams. But the real magic happens when we take the first derivation, fx. In biology, the first derivation represents in the extension growth rate how many grams of biomass the plant is putting on per month. Instead of that, this mathematical curve shows us exactly when the plant growth engine is acceleration faster. A close-up on a peak of derivation curve, a big text to month 6 to month 6.5 is a maximum observation windows. Please, let's look at the data. Our model shows that right around month 6 to 6.5, the growth rate hit its absolute peak, the mathematical inflection point where the second derivation equals 0. At this exact moment, the pineapple is accumulative, a massive 270 grams of biomass per month. This is our field agri-tech action plan. By targeting these exact 6-month windows to deploy our primary NPK fertilizer, we match the plant's highest metabolic demand. The root trim is up instantly, leading to near zero leaching and a guaranteed premium fruit size. In conclusion, by marrying calculus with agriculture science, we move away from traditional calendar-based farming and transition into precise smart farming. Using derivative tell us exactly when to feed the crop. This protect Malaysian peatland ecosystem from chemical runoff, save farmer money, and secure a high yield harvest. Thank you very much.
Hi everyone, my name is ALIA AMIRA binti ABDULLAH, number matric F25A1598, and today I will be present our agrotech simulation project on modeling oil palm fresh fruit bunch year. Summary of the choosing Bioscience problem. The Bioscience problem we are looking at is how to predict and maximum oil palm yields as the tree grow older. Biological oil palm tree chance over time. When they are young, they produce very little fruit. Then they grow quickly and reach a peak production pass. Finally, as the tree get too old, their fruit production naturally goes down. Importance of study this Bioscience problem. Why is this problem? Because running a plantation costs a lot of money. By using math, to treat this biological growth, farm manager can know exactly when the tree will produce the most fruit. This helps them plan when to apply fertilizer to save cost and when to cut down or tree to plant new one without losing profit. Let's look the interactive card. As I move and click along the card, we can see two main lines. The green line, total yield. The tree start producing fruit at 3 years old. The line goes up quickly and hit the highest speed around 15 to 18 years old. After 20 years, the years start to drop because the trees are getting old. The orange line, growth span. This shows how fast the yeast is changed. If I click here, we can see the span hit it Hennes point at 9 to 10 years old. This means the tree is improved its years fastest. And this after 10 years, the span slows down and goes below zero after years 20. Recommendation to make this HTML better. Lastly, to make this HTML web page better, I recommend add an export to Excel button using JavaScript. Even though the graph is already interactive and can be moved around, user cannot save the Excel number. If we add an export button, plantation managers can easily download the asset data point they click into a Excel file for their move report. That's all for me. Thank you.
Hi, my name is Ahmad Syauqi bin Jaafar. Matric number F25B1527. And I am a smart food agriculture student specializing in agrotechnology. Today, I am excited to present AgroCalculate, which is a palm oil bunch maturation and derivative simulator. This digital twin application bridges the gap between abstract calculus, specifically the first derivative, f prime, x, and its critical practical applications in bioscience and automate smart plantation management right here in Malaysia. In Malaysia, the oil palm industry is a pillar of our agricultural economy under MPOB, which is a Malaysian Palm Oil Board standards. Timing is everything. Traditional estates face two major challenges. Firstly is inefficient fertigations. Fertilizers are applied on rigid cycle, ignoring the fruit's actual developmental stage. Secondly, suboptimal harvesting. Harvesting too early results in low oil yield. Harvesting too late increase free fatty acids (FFA), which is severely degrade oil quality. By integrating smart agricultural sensors with predictive mathematical models, we can solve these issues in real time. So we go to the mathematical modeling. To model the weight accumulation of a fresh fruit bunch (FFB), we use a logistic growth S-curve, representing bunch weight Fx in kilograms over x weeks after flowering. So Fx equal to L divide 1 plus e power negative k bracket x minus x0, where L equal to 22 kilograms is the maximum asymptotic bunch weight, and K equal to 0.35 is the growth rate coefficient, and X0 equal to 11 WAF is the inflection point where the growth acceleration peaks. However, the static weight alone cannot guide precision agriculture. To execute precision fertigations, we need to know the instantaneous growth rate. This is where calculus come in by taking the first derivative f prime x we find. We find f prime x equal to L time k time e power negative k bracket x minus x0 divide bracket 1 plus e power negative k bracket x minus x0 bracket and power 2. This derivative tells us exactly how much biomass is being added per week at any specific point in time. Let's see how our simulator translates this math into actionable economic decisions across 3 critical growth phases. Phase 1, which is the vegetative or cell division phase, 0 to 5 walk. At week 4, the bunch weight is only 1.76 kg, which with a derivative growth rate f prime x of just 0.2 kg per week. Biomass accumulation is low as cells are still dividing. The SFA automate system recommends focusing on root establishment with balanced nitrogen and low potassium. Phase 2, the inflection zone or peak zone. At week 11, we hit the inflection point. The bunch weight is 11 kg, but notice that the derivative f prime x reach is its absolute mathematical maximum at 1.93 kg per week. Biologically, this is the most aggressive dry matter deposition phase. The agrotech response is crucial. Our IoT irrigation peaks potassium, K and phosphorus delivery right now to feed this rapid cell expansion. At phase 3, physiology, maturity and harvest at 20 WAF and beyond. By week 21, bunch weight plateaus near its maximum capacity of 21.37 kg. Crucially, the derivative f prime x plummet close to zero, which is 0.07 kg per week. This tells us physically growth has stopped and the fruit is now purely synthesizing oil. The simulator display harvest ready, signaling the harvester that the oil content is at peak premium quality. So, in conclusion, AgroCalculate demonstrates that calculus is not just theory, it is the computational engine behind automated smart farming. By mapping crop growth rates using real MPOB aligned equations, we can reduce fertilizer waste by up to 30%, maximize oil yield, and optimize labor cycle. This synergy between mathematics, biology, and technology is the future of sustainable food security. Thank you, and I am now happy to take any question. Thank you.